All right. So for those still in the PINDER side of the Zoom, we're going to get started in just a moment, going through our little walkthrough notebook that I think in general covers more details around concepts that are already in some of the PINDER tutorials, but it will be a good opportunity to interactively go through the various pieces from up and even include some relevant tips for how to include PINDER in a ML workflow. Okay, and there will be a couple of section breaks where we'll be able to pause and ask questions on the previous sections. So, but don't hesitate to drop questions throughout in the Discord. All right. So I think similar to the PINDER notebook, we're just installing some dependencies. These are optional, but made use of in this notebook. So it's included. I believe the environment should already be pre-installed, so we don't need to, this should be a quick run. So to start off, I guess it's really about how do you get the data set in the first place. We're not going to download the entire data set. It's quite large. I think roughly over a terabyte when uncompressed when you download the whole data set. But there's a kind of lazy, eager downloading that's implemented in PINDER, where if you try to request a system without it being on the disk yet, it will automatically get downloaded. A quick note on that, while it's convenient and definitely useful for the notebooks, I would highly recommend not doing that if you're going to actually train your models, because while there's like a multi-threaded, relatively efficient downloading, you definitely don't want to bottleneck your data loader by file I/O and network bound I/O. So this is recapping a lot of stuff that's already in the README and tutorials, but there's a root directory that gets created by default for PINDER, which would be in like user home .local share PINDER and then a version. So we currently the version is based off of when the latest RCSB snapshot was taken in the ingest, and in the future we may release new data set version. You can, of course, control and download to a different directory, either through an environment variable or explicitly passing it to the downloading function. It can be downloaded through a Python script, or probably more recommended directly on the CLI, where you get a progress bar and it will take a while depending on your network, but once downloaded, will be stored on disk. So as I alluded to in the previous section, I think we in both PINDER and PLINDER, we a lot of emphasis on annotations, both annotations that can be extracted directly from the MMSIF in RCSB, or existing annotation external data sources, as well as things that we calculate on every dimer that we decompose from the potentially higher order oligomer complexes. So we do track that oligomeric state actually. So in the test and validation set, we explicitly limit it to true biological dimers. So the biological assembly is annotated as either homodimer or heterodimer. But for the training set, we are also considering higher order oligomers, but at the moment, PINDER is focused on dimers. So we don't actually have a PINDER system defined as that original higher order oligomer, but rather the dimer decomposition of the complex defined by basically any two pairs of interacting chains in the biological assembly. So I think that's also an important detail. A lot of times you have crystal structures with asymmetric units that you would apply symmetry operators to and produce the true assembly, Classic example would be viral capsids, and all of those types of true complexes are captured. We also, track the resolution, experimental resolution, and method was actually used to resolve the structure. So cryo-EM, X-ray diffraction, amongst a few other methods. We calculate something we refer to as interfacial gaps. Many of you probably have seen structures with unresolved residues, either in a loop, but here we specifically have annotations that calculate the number of such gaps that are proximal to the interface. So in some cases, this may just be one residue missing near the interface, but in others, you could actually have two disconnected segments where there's a large stretch of unresolved residues, potentially from a disordered region that actually is near the interface, but is not resolved in the crystal structure. So again, this type of complex would not be in the test and validation set, but would be valid for the training set and is annotated accordingly at two different radii. We also track the atom types and then use the Prodigy CRIST algorithm to basically score the propensity or likelihood of interaction being biological versus like crystal packing induced. And so in the test set, we use this to only consider structures with probability greater than 0.5 of being biologically relevant. But for every other structure in train, this is available as a annotation called probability. Structural elongation and planarity are two calculated metrics. We can dive into those a bit more, but the elongation is basically a measure of the variance when you project the coordinates onto the largest principal component. And you can detect these sort of long barrel complexes that are often repetitive and might be part of like larger higher order oligomers and may not be relevant depending on your task. I think one of the key points with preserving the entirety of the PDB as to our best ability while annotating them is that you can actually use filters and these annotations to create specific training. So you may be interested in training a model that actually can use very noisy data or is working on specific classes of proteins or domains. And these can be used to either remove or explicitly include certain types of interactions. So we're not going to go into everything in detail here, but in addition to the previously mentioned annotations, we calculate like the effective MSA depth, so that like the number of effective sequences or NEF is calculated for the paired representation of everything in the test set, as well as for the unbound monomers of every other structure in PINDER, and the paired and number of effectors is particularly useful for stratifying performance on the evaluation benchmark set to see how much reliance there is on evolutionary information. The primary kind of data entry point to PINDER, or how you would most frequently interact with it, is probably via the index, and then another data frame that's stored in a Parquet file called metadata. It's really just an extension of the index containing additional fields and annotations, and you may not always need all of these. So we've split them up into the index and the metadata. Index provides the system ID as the primary key. This follows a format where the first, we'll go over an example below, but basically the receptor chain, which is going to be the PDB ID, the chain with the copy number that I mentioned earlier in the chat added, as well as the most represented uniprot. I think it's an important point to make that not all crystal structures are even have a uniprot ID defined for their sequence, and others are chimeric and might be a hybrid of two uniprots. So when you see a uniprot ID for a PINDER chain, it is determined based off of the largest number of resolved residues from the respective protein uniprot ID. These schemas here are for that index and metadata field. It's really, again, just a pandas data frame, but we also expose these pydantic classes, index entry and metadata entry, which get wrapped up in this PINDER system that we'll go over in just a moment, that basically allowed just property access as well as some convenience methods for parsing out some of these other columns. So when we see hollow hollow LPDB, are just the relative file names of the hollow or ground truth bound form of the receptor. It's split into a separate PDB. There's also a PDB which contains the receptor and ligand in the native dimer complex. That would be the ID.pdb. Then when available, we provide an alpha-fold monomer. This was based off of uniprot matching. So for those cases without a uniprot ID defined in the original RCSB accession, or cases of uniprots that are not predicted by AlphaFold, these are not defined, but it does provide a fairly comprehensive coverage. Similarly, there's the APO receptor and ligand PDB, and you'll notice that there's also PDBs, so similar looking column names. The distinction is that when an APO PDB is available for the receptor, the APO-R PDB will the quote-unquote canonical APO pairing. This was done to introduce a single consistent APO pairing when you're considering the test set. So when we're looking at evaluation, we would want to ensure that we're actually comparing the same set of inputs for a given system to assess how well a model is performing on the unbound case. But especially for training use cases, there's obviously going to be more than one in many potential APO structures containing either different sections of the domain in the resolved structure or in different conformations. In the case of PINDER, we define APO simply as any protein chain without any other protein chain neighbor in a very permissive 10 angstrom backbone atom radius, so not just C alpha. And so while there could be cases where you have sort of these disconnected proteins that may have ended up as an APO, for the most part, all cases like that would actually end up being dimers with low interface areas. And so APO monomers are also originally based off of a uniprot accession and then evaluated based on properties like their sequence identity and structural resolution near the interface, so how much of the interface is resolved. In the case of the evaluation, there are certain APO structures that actually get removed or disqualified for test and validation. But one of the things that we came across as an interesting use case was for training, you may want to actually consider noisy inputs. So either learning to ignore non-relevant information or make use of the relevant information that can be gained from a noisy input. So we do know that during inference, we would often, we would not have the ground truth structure. And so we'd have to, be faced with the choice of selecting which structure to use, whether that's an AlphaFold monomer or, one of the many potentially available unbound forms of that structure. And so we actually repeat that APO pairing for the train split and relax the filtering thresholds that were used by basically a factor. And than things that were below this, that were introduced in this lower kind of filter regime are labeled with a low quality label for the APO pairing. And then these are for convenience, so APO-R, APO-L, hollow-R, which these should always be true, predicted R and predicted L are basically Booleans, true or false, whether a monomer exists for that portion. Is there anything else you wanted to cover, Mehmet, before we move on to actually examining the index?
Yeah, I think it sounds good so far. And but if there are any questions, please write in Discord. Until now, there are no questions. But yeah, anytime, please feel free, because this is meant to be an interactive session. So you have the chance to ask anything.
All right, let's dive in then. So like, as I mentioned, I think the most kind of frequently, at least by me, used interface to PINDER is through getIndex and subsequently getMetadata. We're not going to run through every single one of these columns. I do encourage reading the README on the GitHub, which also contains these, as well as the doc strings and the hosted documentation. But here's going back to what I mentioned previously about how the system IDs are defined. We'll notice here the 7RZB was the PDB ID. A was the ASIM ID, and 1 indicates that it's the first copy of the ASIM ID A. So in this case, it's actually a homodimer complex. We can kind of guess that based off of the A1, A2 symmetry here, as well as the uniproduct sessions afterwards being identical. The order goes receptor monomer and then ligand monomer, so right to left or L. And in other cases, you can see like over here, this actually ends up in what we call the invalid split, which I can go into in a second. There's a number of different cases that can result in that, but you could see chain R, chain L are pointing to the 28th copy of the C ASIM strand and the 35th. So this is probably a large assembly with a high degree of symmetry here. Going to the split labels, so we would be able to see, that there's a total of 4 split labels. It's going to be train, test, val, and invalid. So in the case of train, test, val, hopefully that is already clear. Invalid could have happened for 2 reasons. One is it failed to be clustered in the sense that it was a singleton that didn't exist, that couldn't be connected in the graph, or also in the case of deleaking, when we have in the test set, we only keep 1 cluster member from the set of different dimers that fall into the same cluster. For every other dimer that was not selected as the representative from that cluster, those are moved to invalid, because by definition, they, if it's in the test split, it would not be eligible for val or train, and we move that to invalid. Let's look at the metadata, very similar interfaces. There are some keyword arguments that are possible to both of these functions, but more often than not, you just want the data frames, which are also going to be located in this path that was referenced early on in the PINDER location. Okay. So metadata, contains a lot more detailed annotations that are available. So label is just the Prodigy Crist label that is based off of the probability. So bio for biologically relevant and crystal. And then when it's missing, it was something that couldn't be processed by Prodigy. So I'll pause here before we move on, just in case there's any questions before we jump into the PINDER system. Okay. Not seeing any questions yet, so we'll proceed.
Yeah,
Here,
I think
oh yeah, go ahead.
let's wait a bit on in Discord. I think some people are writing
Okay.
there. Yeah, if
Thank
we can
you.
zoom in.
Is that good?
Yeah, it looks good, I think.
Cool. So here's just one, pandas example of how you could, just apply filters and get a subset of the data. Just illustrating a specific example here where, although there's other ways to determine whether it's a heterodimer, I think actually this is kind of an incomplete definition of whether it's a heterodimer, because as mentioned, you could have first of all different isoforms of the protein, as well as undefined uniprots. But here we essentially require that the receptor and ligand have a different uniprot ID. It comes from the test split. And then these are the Boolean columns I was mentioning previously. We're here requiring that both the receptor and ligand have an apomonomer. So if we run this, we'll see the subset of that test split, which is actually only 35 complexes that satisfy that criteria. Sadly, there is a heavy bias towards homodimers in the PDB in general, but in PINDER we do have the PINDER S subset of the test split, which tries to more evenly balance the split between homodimers and heterodimers. So we could grab one of the PINDER IDs, and here's an example from PDB 3VF0 containing these two chains. So another very common entry point besides just the index table is PINDER system, which I would say is probably the simplest interface to get access to structures for a given PINDER system ID. So it really just accepts an ID as a required default argument. And when you create it, it essentially wraps up all of the available structures, the index and metadata into one object that is, we'll go through briefly here. So the entry attribute contains this index entry, which is really just a row of the index, and it has some convenience methods on it, as well as the raw data contained inside of the index row for this system. So these are all accessible, and then you'll notice we're also printing out various structure properties. So this is another very useful base class, which can work on not only PINDER structures, but is definitely PINDER centric here. And we'll see that we have the native, the hollow or bound receptor and ligand, the apo receptor, apo ligand, predicted receptor, and predicted ligand. So in this case, we actually we're lucky, and we just selected a system that had full coverage of all of the monomers. And so you could inspect each of these structures or access them via these attributes. So you can pretty much just rely on holo, pred, apo, and then receptor and ligand respectively. So if we look at the string representation of the holo ligand, we see it's pointing to the actual PDB file path of where this specific mono located, prop map, which is useful if we can maybe go through what actually that looks. I forget what it's in a mapping. While you may not need this, I think it's has been useful. You need to get access to detailed sequence information extracted from the MMSIP. So here you get per residue level. So resolved 0 or 1 contains residues reported in the original RCSB entry, but are not resolved in the structure. And we have information like including the residue in the PDB from PINDER. Always start with 1, and the residue in the PDB as annotated by the PDB, and the author, which can sometimes be identical and in many cases be different. Do 3-letter code, canonical 1-letter code, and then the uniprot code and uniprot accession ID, which can, like I said, contain sometimes more than one within the same structure. Yeah, in summary, these are the most important attributes of the PINDER system. I will also mention that to these, there's another one called aligned holo R and aligned holo L, which for the majority of systems, so coming from train split, holo receptor and holo ligand will already be superimposed to and in their original coordinate frame, how they looked in the assembly in the RCSB. But for the test set, in order to reduce any potential bias from pre-orientation of the receptor and ligand in the bound conformation, we actually apply a normalization to essentially translate it to the origin and flatten it along the largest principal component. And this is done to scramble it. If you ever need the original aligned coordinates of the receptor and ligand, those are available in the aligned holo R structure and aligned holo L, or in the combined native structure. And we'll also go through how you can actually produce such a aligned structure, because these are easily done with the PINDER APIs. So here we're just going to grab an example system that has APO structures and show you some basic concepts of the structure objects in PINDER system. So we're going to actually visualize, in this case, the ground truth structure, and going to create APO superimposed structures and then write them to a PDB file to load in Py3DMOL. So here we saw that previously there was a native attribute, and each structure attribute has a file path, which just points to a PDB file. If you're composing a new structure, it will actually infer a file path based on the combined structure file names from the original inputs. And so that's actually what's going to happen here. 2PDB actually accepts an optional output path to a different file name, but by default, it will basically be the concatenation of the two monomers that were used in creating this. These structure objects have some convenient attributes. We'll go into these in more detail. But for instance, you can get the context. This actually accepts additional keyword arguments like a radius and whether you want to include whether C alpha only contacts or including heavy atoms. And so here, what we're going to do is get that interface, those interface residues, load our ground truth, show it in hot pink and a deeper blue color, load the APO complex we just created, and then select the interface residues of the apo and hollow structure and show them separately. I believe this was actually slightly outdated, so you can actually explicitly specify a model where we want to apply this. So for instance, if we want to only show apo residues like that, we can specify that we only want model 1 to look like that. Alternatively, we can actually load the interface residues. Well, I think for the interest of time, I'm going to skip this, but in a similar fashion, you can get the context of the ground truth complex and overlay them, and you would actually see where there are conformational differences when they're superimposed. So in addition, I think this is a convenient property. We tried to follow conventions in DB4 originally introduced for classifying the difficulty or flexibility of a system based off of how different the unbound conformation is from the bound conformation. So for every PINDER system, you're able to just grab the unbound difficulty of the monomers. And when you have a case where only one of the monomers, like the receptor or the ligand, is available, it will actually use the hollow monomer in place. And so you can get also an assessment of difficulty when you have a mixed monomer. Same for the predicted monomers, along with a bunch of metrics that are actually used in coming up with the final classification label. And we can feel free to ask questions about any of these. So these structure objects have some other convenient properties. Under the hood, these are really just wrapping biotype. You may get sick of hearing how much I love biotype, but it's really awesome if you guys are used to working with NumPy arrays. It's a NumPy centric and NumPy native framework for working with biological structural data as well as sequence data. And here we are basically leveraging some of the utilities there and have a helper method here. You could say, a different type of filter, such as, element mask equals C will be, and we see here the atom array object is actually changing shape depending on what we're filtering. You can actually mutate the structure in place. So by default, this was returning a new copy. But if you say copy false, it will modify the structure. And in this case, we're filtering on name equal to CA. The convenience wrapper that we actually used, but it's essentially a way to combine monomers that might exist. So the APO receptor ligand or predicted receptor to expose them to their respective in the ground truth complex and return a dimer complex containing those. So we saw in the original PINDER system, it was this ID for 3VF0. We see now this APO complex that got created has a PDB file path with 3S5L0H, which were actually the receptor and ligand APO monomers that were used in this specific case. And then we can also, for those who like pandas, get a data frame representation of the structure, which will just take the atom array and cast it to a data frame. So I definitely recommend everyone go through the tutorials on your own time that exist in the PINDER documentation. If you just visit the PINDER repo, there should be a linked hosted documentation. There's some tutorials available that cover a lot. In the most basic way of constructing a loader in training, you can imagine creating an iterator, a generator expression of Pinder system object. That's how you prefer to load it. But we also provide an abstraction that's easier to plug into existing PyTorch frameworks, which itself core, it can be used outside of PyTorch. Pinder loader. It's not necessary, but it provides some convenient ways to apply both filters and transforms, as well as loading specific subsets of data, and even different mixes of monomers, which we'll go over shortly. By default, it's hollow. Here, where the sub filters and base filters, I would also recommend reviewing the document. In essence, base filters are things that take in a Pinder system and return a Boolean, true or false, to pass the filter. The subfilters are used to remove certain monomers, so specific subcomponents of the Pinder system that don't meet the filter. So you could actually the original system while removing, for instance, APO monomer if it doesn't pass the filters. Here we see we loaded the test flow, the Pinder AF2 subset. This is a specific benchmark subset designed to evaluate against AlphaFold 2 multimer without needing to retrain AlphaFold 2 multimer. So it's deleaked against the AlphaFold 2 training set. Here we can now grab an item. So by default in the Pinder loader, each item is returned as a tuple containing the original Pinder system that got loaded, the feature complex and target complex, which is essentially going to contain the target complex, the hollow complex, and the feature complex will be potentially hollow, APO, or a mix, depending on you specify monomer priority. And by default, these are also cropped such that the feature complex and target complex have the same, which is rarely the case by default when you consider the unbound structures, which are completely unrelated to the bound structure. So we can also either items by an index or iterate over it. In this case, we're just going to cap it to 10 samples, but you'll see that the iterator is going to print that it has up to 180 systems to load. Another convenient way of specifying is actually with a specific list of systems. So for instance, we might have applied a query to our index, and the resulting IDs that satisfy that query, we can load that specific subset by just specifying the ID argument. Here we're just going through the items that got loaded, just be 2, and we're checking that did we actually pass all of the filters, and in this case, both systems do. While not required, there is an optional argument to Pinder loader called a writer, which you can use either the Pinder default writer or write your own writer. For instance, if you have certain transformations and rely on PDB file paths that are pre-transformed or pre-featurizing the structures and writing them to PyTorch file, you could, in theory, write your own writer here. And while iterating, you can see that as we go through the loader items, we're just asserting that in the default writer, we write out the monomers to a directory with the system ID as the top level directory. And I'll pass it over to Mehmet to go over the Torch data sets and data loaders in a bit more detail. Again, there's 2 separate notebooks in the Pinder tutorials that I would recommend looking at, but we're going to go dive into this with a bit more hands-on. And I guess before we pause once more, see if questions. I'm not seeing any in the Discord. Oh,
Yep, there's one.
If I want to measure the difference between interactions of chains of normal hemoglobin and its sickle cell variant, how should I go about it? No worries. I mean, I think in general, so one thing we didn't cover here, but it actually does get covered is superposition. So I think if I understand the essence of your question, there's a lot of different ways you can go about it, but I think in the most basic form, you could think of comparing their contacts, so superimposing them and visualizing them, like the apo complex, or for instance, if we don't actually have to only load PINDER systems with this. So when we were, let me just insert a cell here. So we saw our PINDER system stored in PS. If we say, for instance, create apo complex, these structure objects themselves actually respond to a superimpose method. And you'll see that that returns RMSD values as well as the superimposed apo structure. And so if we were to think about earlier when I was showing the example where we loaded them in PyMol or in Py3DMol, we can get contacts and interface residues, which I'll show here. I think the full demonstration of this question might go a little over time here, but I will try to just briefly answer. Conceptually, we would probably superimpose them and then look at the interface residues. We could do the same thing for a hollow. I'll print out both apo contacts, hollow contacts. Now, the residue numbers are not necessarily going to be, oh, sorry. Are not necessarily going to be comparable. So when comparing structures, so PINDER actually provides a evaluation harness, which we'll go into in more detail. In this case, it does seem that they are numbered similarly. You can see that the interface residues, so the receptor chain residue 114 is in contact with residue 263, 264, which probably does follow different residue numbering in this specific case. There's ways to visualize, the sequence alignment itself. I would recommend checking out the biotype tutorials. And then, of course, you can get much more granular in comparing specific interactions, like actual hydrogen bond networks and other intermolecular interactions. Hope that answers some of the question, but of course it's a much more complex topic. I think an example would be you could actually load those two PDBs. So one thing I didn't show is structure just accepts a path to a PDB file. So if you had your sickle cell variant and the normal hemoglobin, you could load those, superimpose them, look at their interface residues, perform a sequence alignment. All of this is exposed in the PINDER package and biotype package. Hope that was helpful. And at this point, I think I will pass it over to Mehmet.
Yeah, okay. Yeah, and then at the end we can go back if there are questions at any point for the parts that Danny just showed as well. So yeah, feel free to go back and ask anything. But I can share the screen, maybe, Danny.
Yep.
Okay. Yeah, if you can give me the permission, I think.
Yeah.
Yeah, thank you. All right. Yeah. So one of the things that we wanted to show here in this tutorial was to have like end-to-end kind of example pipeline that you can start from and inspecting like the systems, loading your data by applying some filters, and then going through the training process as an example, um, um, to show some of the available um, PyTorch-based data loaders that we have built in PINDER. And then finally, to show how this ends up in the evaluation part, the PINDER eval package. So there are right now, as Danny showed, we can use the PINDER's own loaders, which is the iterator, like the PINDER loader plus the iterator that Danny showed. But in addition, we also implement PyTorch geometric and PyTorch dataset-based data loaders, and also, well, datasets and data loaders as well. And you can find more about it, of course, in the repository. But here we wanted to show the PyTorch-based one. So essentially, we have here still the integrated PINDER system that the PyTorch dataset class kind of iterates over, makes use of to obtain like there is like a defined get item that it implements. And so all that is done. So it should be fairly easy to plug into any PyTorch based model. And then also, as Danny mentioned, the cropping in terms of like the aligned residue to residue correspondence between the targets and the feature complexes. Those are also handled. And in addition, all the collation functions as well. Then we also have a couple of details on like filters and transforms. So that I'll go into more detail. So, but in general, what the dataset returns along with the like the dataset essentially returns the target and the feature complexes, and in addition to this, we have also the collation functions and the data loader ready implementations as well. So going to more specifics of the data set. So with the more specifically, so we have the target and feature complexes, so that contains more of the structural features and the amino acids and so on. And then we have the ID for the PINDER system ID, and then what I said also about the batching, that we have the collation functions that which essentially first converts the structures to tensor formats. And this is our implementation, but yeah, you can also modify all this by adding your own transforms and output. So I think it's a good basis to start with. And then, of course, you can go into more detail within the API. And in addition, I recommend checking out the PyTorch geometric dataset as well if you heavily make use of graph representations. So here, let's start with the code. So here, essentially, this showcases like having some quality filters. So for instance, if you would like to only use the X-ray structures and better resolution ones, and then the physiological interfaces, then you can use these kind of pandas queries to just sample your data. Here we are just sampling a subset as a test case. So here we sample like 10 of them, and yeah, we can also denote the split. So it samples from train, validation, and test splits. And for the test, we'll just go through one example to just visualize and show the end result from the evaluation. And here we have the first set of filters, the base filters that Danny talked about. They're the same ones that the data loader accepts. So in this case, we are handling the things like, again, quality related filters that are done dynamically. So the ones above are done on the index metadata that's already present, but you can implement your filters which are dynamically computed on the samples from your dataset. And these are based on this at system level and subsystem level. So that's like individual monomers in the systems. And yeah, so you can go into more granular detail in filtering. And then finally, we have transforms that takes your structure data and does something with them. So usually this is something like you select a particular type of atoms. So you can, for instance, select just the C alpha and so on. And then, so this is the target representation, right? So this is what we want to predict. And these will give you essentially the bound target representations. And for the feature transforms, we do it a bit differently. So here, as an example, we're selecting the same kind of atom types, but then we apply a random ligand transform so that it basically randomizes the input ligand pose. And yeah, these are going to be our features. And so here we essentially load the subsets for the data sets. And yeah, so it's 10 for each, and then 1 for the test. Yeah. So then in addition, we can adjust some parameters like the monomer priority. And here essentially you can prioritize your sampling towards APOs and yeah, do those kind of adjustments. And then there is also the fallback to hollow. So when it's not available, basically it falls back to the bound structures, and this can be enabled or disabled depending on your use case. And of course, yeah. So for training, this kind of variation in sampling it benefits a lot of the flexible docking algorithms, and yeah, so we basically provide this easy to access this kind of augmentation on the go and adjust the level of what you sample. And in addition, we sample from clusters as well. So that's one of the, so when I go to the data loader part, I'll also talk about that. But then we have here just one data set, a data item, just to show what's being patched. So the feature complex essentially, yeah, contains all the atom coordinates and so on. I think I showed it up above as well, but feature complex identical for this, but only the ligand randomly transformed. And then here, yeah, you can essentially see all the keys from there. But yeah, so these are what are basically correlated. Yeah, all these can be accessed in the batch essentially as tensors. And yeah, we can see the class here for, let's see. Yeah, so let's continue from the data loader. And here the default collate function that we implement can be essentially given to form this PyTorch data loader. So this is essentially calling and building from the default data loader from PyTorch. And so then you have all the parameters available for that. And then here we're showing just the same things that we just saw. So I'll go a bit fast here so that we can get to the evaluation part. So because we provide this dummy model to show how the model would fit in. So here it's just a basic model that we put in, which takes the ligand and receptor coordinates and has a single cross attention layer to predict the rotation and translation, which is like a really simple model just to make use of the batch that we have. So it takes as input the batch the object that I showed you, which collates all the coordinates and so on, and it then use that to predict the rotation and translation matrices. And from here, it exposes basically those matrices that we're gonna use also in inference to apply and write into PDBs. And this is solely also a redocking kind of prediction. And so yeah, as an example, and here it also returns the ligand coordinates that we can just take it and use with an MSE loss to just to have it end-to-end running until the evaluation. So here we define our model with really basic, with really small dimensions so that it runs. And then here just validation and train loops. And I don't think it's interesting to talk about this. So then we have our data loaders, same as the train, but here essentially we have, well, actually I'll stop this because it takes a while. And then essentially this has instead no shuffling, just to keep the order, but apart from that, it's the same. And here we have like, yeah, Danny, you want to?
No, I was just gonna say, I think actually with 5 epochs, it's fairly fast if you want to let it run while you keep talking.
Yeah. And yeah, actually I ran the one before it. So for the MSC, I mean, this is of course the worst kind of MSC loss that you can get, but just to showcase that, yeah, normally you would yeah, hopefully expect a much smoother loss there. But just to connect things to now to the test inference. Yeah, so this is the interesting part. So then we take that single test that we sampled previously, and then we can take that and then load it and do the inference. I think I'll stop it. Yeah. So we do inference for just that to get the coordinates, and we can actually access the index that's stored inside the test loader. So this is going to be, of course, many more cells, but then you can see essentially you can access all the details here as well if you want to stratify or look into what kind of test data you've loaded. And here we're just taking the index, it was just a single one, and then we can here just load load it at structure level, so that we can inject our coordinates that we predicted into that structure. So here we specifically select the ligand chain, and because we are predicting the ligand, so then we inject the ligand coordinates into there, and then we use the structure module from Biotite here to essentially apply the transformation. And then after this, we can write it on the disk and just visualize. And yeah, you can see that the prediction is really off. And we can validate this also by running this through PINDER eval. And here the docu is based on the Biotite docu, which I think Danny can give more details, but it's highly optimized using I think Rust in the back. So then, yeah, it's pretty quick in that sense when you run like thousands of servers. It really matters. So then we can see all the details that we have as an output. So here we have a single test system. And so this is at system level. Then we have also outputs, or a leaderboard kind of outputs at higher level that it summarizes like the acceptance, for instance, Capri acceptance percentage and so on. Or if you want to look at the median RMSD or for a set number of models that's ranked, then you can look into all those details as well. But here in the single system output, since we only predicted one model, then that's the name. And then we can look at the decomposed dog-Q metrics. So all these three are components of the dog-Q, and also the Capri classification. So then there are some further details on the contacts. So the decoy contacts are essentially the input, the prediction contacts, and compared to the native holo. And finally, this is how it actually works. So this is just one system that we manually evaluated, but you can ideally have like a number of models that you might have ranked for each system, and as long as you write it out in this format that for each system you have the apo decoys, holo decoys, and predicted decoys, depending, of course, if they're available. And you after you rank it with if your model also takes care of that, you enumerate it in terms of the rank, and then from there it gathers the metrics. And Danny, if I missed something, feel free to.
Yeah, I'll just add, I guess one thing some people ask, you don't have to call it model 1, model 2, etc. The other folder structure is required to go through the eval entry point, but really you just basically there needs to be a number structure. It has to pass that regex that's shown in the text below the cell.
Yeah.
And as long as it will pass that, so essentially a number, it can be 0 based, 1 based, doesn't matter, but it will be in increasing order. So top ranked would be 0 or 1, and then so on. And those are actually used in determining like Oracle top 1, top 5 predictions in the eval. And I guess the one thing like here where the warning sign is by default, if you don't include allow missing as a flag to eval, it expects that you're evaluating on the PINDER test sets. So there could be, PINDER XL, PINDER S, PINDER AF2, and each of those subsets has an expected number of systems that are holo, apo, and predicted monomer inputs. And in order to make it a person, let's say your model can't handle larger complexes or just predict a specific complex. Currently in the evaluation leaderboard, by default, these are actually penalized, where basically you can't just not predict a system and still have equal performance. And so those are essentially treated as incorrect predictions if they're missing.
Yeah, and if you use this allow missing flag, then it doesn't penalize it in the leaderboard. So that would be useful to see.
Yeah. And I'll just add, I guess, these are PINDER eval is most useful if you really want to compare to, like, for instance, some of the methods that we reported in the preprint where we actually benchmarked against these test sets. But the previous and that's where you would use either script or this method metrics class. For people who just want to get evaluation metrics either for one model or a list of models or for non-PINDER structures, the most simple interface would be the previous one that was called biotype.q, which accepts basically a native and then either one model or many models. And then you can actually specify your own chains, but by default it will, I think, assume that their receptor and ligand are and L. And you can actually handle structures, but I'd recommend looking at some of the tests or examples in the eval notebook for that. So it's really just based off of the original .q paper, but and yeah, as Mehmet mentioned, fast PDP for file IO, which actually makes a very big difference if you have like 100+ predictions per system per monomer type.
Yeah. Then yeah, I think that's mainly it, and we can show also here the leaderboard part, and so this would be one of the rows. Let's see. And then assuming that you would have not just a single but many test samples here, it's everything is summarized in this leaderboard. So yeah, then you can say like the interface RMSD, so top one meaning the top, isolating it to only the top ranked model, and then maximum of top 5 and so on. And finally, the Oracle independent of ranking. And then we have this for decomposed for each metric in .q, and yeah, you can essentially compare multiple methods. So this is the dummy model, but you can have like 10 different models and summarize it in the leaderboard. So this is all wrapped up and ready to be used. And yeah, so then we can, I think, take in questions at this point for any section.
I see there's one question for the challenge. Are there specific base filters or sub-filter settings we need to follow? Will you provide the torch dataset and torch data loader we can use for the actual training? Thanks.
Yeah, I mean, these are already provided in the repository. Of course, you can make use of this code. That's why it's there. And the filters depends on you. We just make sure that we don't have, leakage, contamination between different splits, and that's the most important part. And there are no rules for filters. And we wanted to keep, so that was one of our points, like philosophy, let's say, that we want to keep as much as possible, even if even if the data is not ideal. You also have crystal contacts in there and so on, but everything is annotated, so you can write your filters and choose the highest quality ones, or if you want to train it with everything, if that benefits your model, then you're free to use anything. So
With really
it
the
all
only exception being just, you can't use the invalid split in training or the test, and basically the normal rules for ML training based off of the split labels is really do whatever your heart desires. And even I think we laid out some rules about external data augmentation, but aside from that, everything provided by PINDER is fair game.
Yeah, external data augmentation. Yeah, just to be clearer on that, the rule is that like you can make use of what we provide for the AlphaFold predictions, but nothing in addition to that. So I think that was the main rule that we have.
Yep. Any other questions from anyone on the call? Please feel free to drop in the Discord, or if there's anything you just would like to know more about or see in greater detail. Well, a few minutes.
Also, just to mention that again, because I think it's important. So the part of the data loader, like this sampler itself, so there are also examples in the repository itself, but we also provide the cluster labels, so you can sample proportional to the cluster size, so that you sample a more diverse train set. So I think that's also an important point to take into account while training. And yeah. Any questions? I don't know how we are doing with time. I think, yeah, we have plenty of time for questions.
Did anyone have any trouble following along in the notebook or running anything, or otherwise Pinder woe related?
Yeah, I think we covered everything, right, Danny? I mean, we can also take questions maybe regarding anything in Pinder, also the splits and those kind of details as well. And since we have time, not just the API that we showed, similarity methods and so on. But of course, it's also in the Pinder publication preprint.
We have another question. So if setting monomer priority to random, does that mean in training it can access APO predicted or hollow structures? I can take this one. So yeah, roughly, yes. Maybe Mehmet, you could scroll to that section where monomer priority is covered. There's two styles of random sampling. If you set to APO, let's say you prefer APO, it will, with the default fallback to hollow, it's going to choose hollow when an APO is not available. But if you set it to random, it will try to, it will randomly sample from the available monomers that are available in both receptor and ligand. So if there was a case where there was an APO receptor but no APO ligand, it wouldn't ever select APO for that system if you use random. Random mixed allows random sampling of monomers for receptor and or ligand from any of the available, including hollow. And hopefully that answers your question. So that's actually a nice way with the random mixed option to be able to really kind of traverse the combination of possible monomers for the system. In addition, there's this flag we didn't cover, the use canonical APO. By default, it's true, but you could actually set that to false to specifically sample from the available alternative monomers. So when we covered earlier, there's like potentially multiple and in some cases, very many pairings available for a monomer. And so that would be one way to try to force alternative sampling. And I recommend looking at the documentation for this, but there's yet another option where if you wanted to pre-specify monomers to use for specific systems, there's also a keyword argument where you can actually explicitly write out for each system what monomer to use.
And one thing to add in terms of the type of monomers. So for instance, with hollow, and actually everything is kind of superposed also to the native when you load it initially. So then I would say that that's something to be careful that you don't give basically the target ground truth to your model while training, because then you'll measure the performance pretty good and for the training metrics, but then for the validation and test, well, I think specifically test, then the performance is going to be pretty bad. So just to take into account that, that's why also we use the random ligand transform here, but you can use any kind of randomization here. I would say you can also rotate the system, or make sure that you're not always you're not giving the target into the model, and you have some yeah